If we want to calculate Laplace transform of t raised to r, by the definition of Laplace transform, it equals to integral from 0 to plus infinity e to a negative st, integral from 0 to plus infinity e to a negative st t to r dt. So what we'll do is we'll do substitution. So we will call that expression s to be t as a new variable st, then du equals to s dt. So after substitution, we're going to get integral from 0 to plus infinity e to a negative u. T becomes u divided by s. And extra factor 1 over s. U. We're going to get, we can factor s is outside, so we're going to get 1 over s to r plus 1 outside. Inside we have integral e to a negative u to r du from 0 to plus infinity. And look at this guy. Well, we're going to call that special expression to be gamma function. So we're going to call that expression gamma function and of r plus 1. So let me give a couple of definitions. Definitions. A gamma function gamma of r is defined as gamma function of r integral from 0 to plus infinity e to a negative u to r minus 1 du. And as we just saw a second ago, from here we're going to get the property of a gamma function, which tells us that in order to calculate Laplace transform of t power function t to r, that's going to be equal to gamma function at r plus 1 divided by s to r plus 1. So that's a property of gamma function that we're going to be using to calculate Laplace transforms. And one more property of gamma function is if we want to calculate gamma function of r plus 1, we can write it as integral from 0 to infinity e to a negative u to r plus 1 minus 1, so u to r du. Then we're going to do integration by parts, so we're going to get e to a negative u to r from 0 to infinity plus integral 0 to infinity r e to a negative u to r minus 1 du. So substituting here upper and lower bound, we're going to get substituting infinity, we're going to get e to the negative infinity, so the whole expression will be 0. Substituting 0 for u, we're going to get 0, so we're going to get only the integral left, so we're going to get r. We can factor r out, and you notice that is gamma function at r. So we get property of gamma function of r plus 1 equals to gamma function at r. Okay. Now let me try to use that gamma function in one example. Say somehow we know that gamma function of 1/2 equals to square root of pi. So what we want to do is we want to calculate Laplace transform of t raised to 1/2. So by the formula which we obtained earlier, Laplace transform of t raised to 1/2 equals to gamma function of 1/2 plus 1 divided by s to 1/2 plus 1. And we're going to get s to 3/2 on the bottom. Now, to calculate gamma function at 1/2 plus 1, I'm going to refer to this formula. So, I forgot to put r here. So gamma function 1/2 plus 1 equals to 1/2. Gamma function at 1/2. So we're going to get 1/2. Gamma function 1/2 is given to us the square root of pi divided by s to 3/2. So finally, Laplace transform of t to power 1/2 equals to square root of pi divided by 2 s to 3/2. Just one more example. Find Laplace transform of t to 3/2. As we did before, in order to find Laplace transform of t to 3/2, that equals to, again, using that formula which tells us to what is Laplace transform of power function. It's gamma of r plus 1 divided by s to r plus 1. So we're going to get gamma function of 3/2 plus 1 divided by s to 3/2 plus 1. Now to find gamma function of 3/2 plus 1, we're going to be referring to that star formula. So we're going to factor 3/2 out. And we're going to need to find gamma function of 3/2 divided by 3/2 plus 1 in the power of 5/2. So gamma function of 3/2 is going to be 1/2 plus 1. So we're going to get 3/2 times 1/2 times gamma function of 1/2 divided by s to 5/2. So finally, we're going to get Laplace of t to the power of 3/2 equals s to 5/2 on the bottom. 2 times 2 going to give 4. It's also in the denominator. 3 and gamma 1/2 we were told is square root of pi. So that will be Laplace transform of t to 3/2. And before we calculated Laplace transform of